Right, so I'm going to describe how I solved a Google coding interview from Mr. Clement Mihailuscu, a Google coding interview with a normal software engineer like myself. So I thought I'd give it a go myself. So let's start with trying to explain what the task is. So the task is that you are supposed to find an apartment to rent, and there are a couple of different things that you want to have close to yourself, such as a gym, a school, maybe an office. Could be more things. So you want to optimize the apartment you pick by looking for an apartment that will be as close as possible to all these things that you desire. So you will be given sort of a list of dictionaries that describe, well, blocks or apartments on a street, and you will be given a list of your requirement things that you consider important. So while I was doing this, I thought of a couple of follow-up questions. So is it safe to assume that all of the requirements in your requirement list are equally important, or is the first one more important and then the second, the third? No answer to that in this video, so I assume that yes, they are equally important. Another one that I thought of was that could there be a setup where one of the requirements we're looking for is missing, like there is no school or there is no gym, and I think that they answered that in the video with a no. There's always going to be an entry for everything that's in the requirement list. And some further things that we got from the video is that there could be any given number of requirements, so it doesn't have to be just gym, school, store, it could be more. Yeah, so this is a sort of an example input here. So you have a list with dictionaries. We have if this location, does it have a gym at this location? Does it have a school, a store? And then we have a requirements list, the things that we want to have. So in the video, it's mentioned that the expected output for this particular one is index number 3, which is this one, or 0, 1, 2, 3. This one is right, false, true. Yeah, so this one. So what I'm going to come up with is one that actually gives you this one. So as it turns out, multiple locations here are equally good. Yeah, so let's just dive into it. So I have a driver code here where we set up the blocks, like the street that we have, and then we have another input, which is the requirements that we have. And then I chose to add some debug prints for this, so that if you want to run this and test it out yourself, you can see some nice debug prints, and we'll use it while going through this thing. So let's head over to the function that finds the best apartment here. So I've written down some of the thoughts that I had when I did solve this task. For me, it took about half an hour, maybe a little bit longer, to come up with a solution. It's not as polished as this. There might be some syntactical errors in it, but I think in general it does solve this problem. It's in the repo as well. In the sketch version, there's a text file if you want to have a look at that. But so what my strategy is to go through all of the blocks that are available so basically all the apartment blocks. And for each one, we calculate a score. And that score is based on the minimum distance that you would need to travel in order to reach all the items on your requirement list. Yeah, so we take this list of dictionaries, and then we take our requirements, and then I set up a vector here to store the score of each block that we come across. So here we have a loop that goes through this list of the blocks, and then we start off with we define a vector here, which is the requirements that we could not find at the block that we are on. And then we go through all the requirements that we have, and we check, is this requirement, is the gym or the store at this block? If so, we give it a score of 0 because we can reach it immediately. And if not, then we note that, okay, this thing we could not find at this location. And then we have a little bit of debug code here. And now we will have to go through the things that we could not find at this location. And we want to find the one that is the closest. I called it the smallest next here, but it is the closest one. And what we basically do is we iterate through the blocks again, and we check that we're not looking at ourselves because we don't really need to. And we don't need to check ourselves. But we do need to check the other blocks. So what we do here is check all the other blocks and see, okay, could I find, say, the gym here? If I could, then we note the distance to that location, to the gym, from the apartment that we are looking at. So that is, if it's above us in the list, we would have to, so this is the index of the apartment that we're looking at. So if J here is smaller than I, it means it's before us in the list, and we have to subtract here. We have to do I minus J, otherwise we do J minus I to get the distance. And then we have a Boolean here. So if we never found anything, we're like, this is the first thing we find, then we record it as the shortest distance here. But if we have found it before at some block, then we do a check. So we're looping through all of these, and then we do a check. So it's the distance from the next block that we're checking. Is it shorter than the one that we have found before? If so, we update the smallest next to that one. And then we just do that through the entire input blocks here, which is all the apartments. And now we will have found the shortest distance to one of the requirements. And then we add distance here to the score for this apartment. And we do that for all the requirements that we couldn't find at the apartment. Okay, so that will leave us with a, let's see where this is where the whole loop here ends. And now we will have a block scores here, which is as the entry for each block, the score, the total score of that apartment. And since this list isn't sorted, we need to iterate through it to find the one that has the lowest score here. We might be able to get some performance gain here if we use the quick sort or something for this. That would probably be faster. But when you only have 30 minutes to solve a problem, you kind of go for the brute force. So we just iterate through and note the smallest possible here. And then we note what the index that is, and then we'll return that. So that will give us the block that is the shortest. Okay, so if we run this, let's see if we have it here. Okay, let's remove it and build it. So if we run that, now I'm running it with the debug prints enabled here. So first we get the entire dictionary here, a list of dictionary, and we get the requirements. And then I kind of wrote down what happens for each block here. So start at block 1, then block with index 0, block with index 1, 2, 3, and so on. So what we do here is we note, okay, which requirements could we not find at the first index here. Look here, there was no gym and no store, so we need to find those. And then I wrote down, okay, how much distance do I need to travel to reach the gym? Okay, I need to travel 1. How much do I need to reach the store? Okay, I need to travel 4 because the store is, there's no store here, and there's 1, 2, 3, 4. So we can see then that the total score for this apartment will be 5. And then we just do the same thing, of course, for all these entries here. And that's what we print out here at the bottom. So we have 5, 4, 2, 2, 2. And there are actually 3 that are equally good, depending kind of how you look at this. But so the first one is this one's going to find, okay, the best block is the one with index 2. So let's have a look at that one and see if it makes sense compared to the one with index 3, which is the same. So block with index 3 is 1, 0, 1, 2. So it's this one. So what we see here is, okay, at this spot, we got a gym and a school here. So all we need to find is, for these two, the gym and the school, the score will be 0 because we can reach them immediately, right? That's what we're assuming here. But we have to be able to travel to we need to travel to the store. So, okay, how far is it from this one to the store? Well, it's 2. 1, 2. It's down here is the store, which we can also see here. That the store and then this store is 2. Okay, so what about this one? 3, the one that's suggested in the video. Okay, we can reach the school immediately here, but we can't reach the gym and we can't reach the store. So when we start out, of course, we're 0 here. So in order to reach the gym, we need to travel 1. So that's 1. In order to reach the store, we also need to travel 1. So that's a total score of 2 for this one. And then I guess it is the same for the last entry. So here we have school and store here. And in order to reach a gym, though, we need to travel 2. 1, 2, in order to reach that gym. So these 3 are equally good. Now, you might be able to argue that actually index 2 and index 4 are better because you have 2 locations right at where you are. So you don't really need to travel at all to reach these. Whereas these ones, you need to travel in order to reach the gym and the store. But that's sort of a discussion, what is better there. It was very interesting doing this task, but when you do it, I have to admit that I felt quite stressed in order to find a solution. I'm sure that you can do one that is better in terms of performance. if you have a little bit more time to do it. But it was still good fun. I liked it, and I hope you guys enjoyed watching this too. I'll of course post a repo so you can have a look at all the code yourself. All right, thank you very much for watching.